Okay, so let's talk about related rates. So when we're talking about related rates, we're going to go back to implicit differentiation. So consider the curve defined by our function here. We want to find dy over dx. So we're going to take the derivative of everything with respect to x. Keeping in mind, when we take the derivative of y, we also need to use chain rule, multiply it by dy over dx. Then we need to get dy over dx by itself. So if I move some stuff around, and factor out, we get 2x plus 5 divided by 3y squared plus 2 equals dy over dx. And depending on what we move over, so if I moved 3y squared to the left side and moved everything else over, my signs might be different. But as long as all of the signs are different than what I have here, we are okay. So we found dy over dx because we differentiated with respect to x. However, we can kind of differentiate with respect to whatever variable we want. With related rates, we're going to eventually use time for a lot of things. So if I have a equals pi r squared, and I want to differentiate with respect to t, we have dA over dt equals pi is a constant. So if I take the derivative of r squared, we have 2 pi times r times dr over dt. So we just need to make sure that we're following that implicit differentiation rule and doing the derivative with respect to whatever variable, in this case, t. We have a squared plus b squared equals c squared, differentiate with respect to z. So we have 2a times dA over dz plus 2b times dB over dz equals 2c times dz, dc over dz. We can also look at this and say, hey, there's a 2 in common with all of these, and get rid of it to kind of just simplify what we are looking at. And then our last one here, v equals 1/3 pi r squared times h. Differentiate with respect to t. So we have dv over dt equals, I'm going to keep 1/3 and pi together, or pi over 3. We need to use product rule. So u prime times v minus plus v prime times u. So 2r dr over dt times h plus dh over dt times r squared. I can go ahead and multiply out the pi over 3. I can also pull out an r if I really want to, but there's not really a reason unless we need to. So when we have two variables that are related to each other, affecting each other, we kind of look at things in different ways. So in math, two variables are related if one variable affects the other. We see this in a bunch of different formulas. For instance, that first one, the area of a circle, we see that the radius and how the radius changes affects what our area is. So if r is increasing, our radius is getting bigger, our area is also increasing. But how fast it's increasing compared to the radius is what we kind of don't know and what we might want to figure out. That's why we look at what's called related rates, because they are rates that are related to each other. So the circle above is expanding and contracting. Find an expression for the rate that the area is changing with respect to time. So we are looking at the rate the area is changing. So we want to start with the area of a circle because we're dealing with a circle. So we have A is equal to pi r squared. And we want to do it with respect to time, so t. So we're going to take the derivative with respect to t. dA over dt equals 2 pi r dr over dt. The radius of the circle is increasing at a rate of 4 centimeters per second. At what rate is the area of the circle increasing with respect to time when the radius is 7? So if we look at our circle here, we kind of already have a picture. So things that it told us, our radius is 7, so this is 7. The rate the radius is changing is, we are looking at our rate, so the rate the circle is increasing by, our radius is 4 centimeters per second. So our radius is getting bigger at 4 centimeters per second. Okay, so we are going to use that equation we just found. dA over dt is equal to 2 pi r times dr over dt. Things that we know, r is equal to 7 centimeters. dr over dt is equal to 4 centimeters per second. So we have dA over dt is equal to 2 pi times 7 times 4. So we have pi that we're going to kind of leave there for a second. We have 2 times 7 times 4. 2 times 7 times 4 is 56. So we have 56 pi. At what rate is the area of the circle increasing? The circle is increasing. The circle's area is increasing, and we know that for sure because it's a positive value, at a rate of, our exact value would be 56 pi, but we also know that 56 pi doesn't mean a lot to a lot of people. So if I were to multiply that out, I get 175.929. Our units would be centimeters squared per second because it's an area, centimeters squared per second. And that comes from the fact that we are multiplying centimeters times centimeter squared. When the radius is 7 centimeters. So we're kind of looking at these different parts and pieces and kind of putting together what we have. A lot of times with related rates, we need to look at what we're deciding on. A lot of times it's a shape, and then deciding what function or what equation formula is the thing that's going to help us the most. The area of the circle is decreasing at a rate of 10 centimeters squared per second. What is the rate? The radius is changing when the radius is 3 centimeters. So we now have our circle. Our radius is 3 centimeters, and our area this time, so this inside part is decreasing at 10 centimeters, so negative 10 centimeters squared per second. So we're going to use that same equation, dA over dt equals 2 pi r dr over dt. This time we have r, which is 3. We have dA over dt, which is negative 10. So we are going to kind of move some stuff around to get dr over dt by itself. So we multiply these together to get 6 pi, and then we are going to divide. So we have negative 10 divided by 6 pi is dr over dt. dr over dt is a radius, so we know that these units are going to be centimeters, but it's a rate. The radius is changing, so centimeters per second. When we are taking and putting this in the calculator, we need to make sure to do 10 divided by the quantity 6 pi, or 10 divided by 6 divided by pi. So the radius is changing. It is specifically decreasing because it is negative at a rate of 0.53 centimeters per second when the radius equals 3 centimeters. So there are some things that we can always do with related rates to kind of help us out. First, drawing a picture. So when we are looking at these pictures, things that we want to kind of keep in mind is that we are going to have static variables and dynamic variables. Static variables are the variables that are going to be consistent. They are not changing. They are just going to be the same every single time. Dynamic variables are ones that are going to be changing. They show movement. It just kind of depends on what you want. So finding the area as a movement is a little bit hard than finding like the radius. We can use arrows to kind of show which direction it's going. Translate the information given to you from the problem and label it on your paper. We need to look at units. We need to be careful about signs of things. All of those kind of pieces that we have in our problem, we kind of have to take into account. Write an appropriate equation to model situation, if not already given one, based off of whatever shape we're given or situation we're given. There's going to be an equation that's going to work for us. Differentiate with respect to time, and then plug in what we know. So every single time with the related rates, we can kind of follow these different guidelines. We're going to continue with related rates and different types of problems as we look at more related rates problems.